Okay, so yesterday we were discussing osculating plane to a space curve. So let me recall what we had done yesterday. So by definition, an osculating plane to a space curve r equal to r s is a plane which has a contact of order at least 2 with the curve. Its equation comes out to be r minus r 0 dash r 0 double dash equal to 0, where r 0 means r at the point corresponding to the parameter s 0. So, this is the equation for osculating plane. If you want to convert it into Cartesian form, in Cartesian form the above equation looks like this: x minus x 0, y minus y 0, z minus z 0, x 0 dash, y dash 0, z dash 0, x double dash 0, y double dash 0, z double dash 0 equal to 0. Okay. Where small x y z are the component of the position vector of an arbitrary point on the curve, and capital X y z are the component of capital R, which is the position vector of an arbitrary point on the osculating plane. So, this is x s, y s and z s. Now, this equation, if you look at it closely, you can rewrite it as r minus r 0 dot r 0 dash cross r 0 double dash equal to 0. So, you will say that osculating plane is a plane whose normal vector is this. This is the vector normal to the curve, normal to the plane, normal vector to the plane, osculating plane I mean. And therefore, these two vectors r dash and r double dash are the vector which generate this osculating plane. You see, if you have two vectors a and b, then their cross product is a vector which is perpendicular to a and b both. So, what you notice is that this vector a and b would lie in the same plane. I mean, r dash and r double dash are the vector which lie in the osculating plane. So, this is an observation that r dash and r double dash at s 0 lie in the osculating plane. This is an observation here, and why I am saying that these are the vector which lie in the osculating plane? Because this is a vector which is perpendicular to the osculating plane. Moreover, these two vectors are orthogonal to each other. This is also easy to observe. Look here. Oh. In fact, r dash and r double dash at any point are mutually perpendicular, The reason is simple. The reason is that in fact r dash is a unit vector, because r dash is a unit vector. That means, if I consider the dot product of r dash with itself, it will be 1. And if I differentiate this, so differentiating this relation, I will be getting r dash dot r double dash equal to 0. Is it right? And this would mean that r double dash is perpendicular to r dash. So, these vectors are perpendicular to each other, and therefore, they are linearly independent, and any two linearly independent vectors generate the plane. Two linearly independent vectors always generate a plane. So, in other words, what I am saying is that the osculating plane is generated by these two vectors r dash and r double dash, because r dash I have proved in the beginning itself that it is a unit vector. This is a fact which we know from the beginning, that r dash is a tangent vector which is a unit vector. Then it will not happen, but our r dash is a unit tangent vector. All right. So, from here I would say one of the important observation is that the osculating plane is generated by the two vectors r dash and r double dash, and r dash is the unit tangent vector. This is something which we already know. All right. So, if you have a space curve like this, then r dash is actually tangent. This is in fact the tangent, and which we also denote by r dash, and the r double dash will be a vector perpendicular to it. So, this will be a perpendicular vector to r dash. So, this is r double dash. So, our plane will contain both of them. So, our osculating plane will be like this. This is the osculating plane. All right. And it has the highest order of contact. All right. Now, we move on to Frenet Trihadron. So, there is a collection of three vectors, we call them Frenet Trihadron. So, Frenet Trihadron. Frenet Trihadron is a triplet of three mutually perpendicular vectors, which we associate to every point of the curve. So, what happens is that if you have a space curve, then you associate to it a set of three mutually perpendicular vectors. We will be denoting them by unit tangent t. There is another vector, another unit vector, I will be calling it n, and there will be a third vector which is perpendicular to t and n both, I will be calling it b. So, this is a triplet of three vectors. When you move along the curve, these three vectors will also move along the curve. They will remain perpendicular to each other, they will remain unit vectors, but their direction will be changing all the time. So, a Frenet trihedron consists of, it is not a proper definition, just a rough definition. A Frenet trihedron is a triplet of three mutually perpendicular unit vectors. Is a triplet of three mutually perpendicular unit vector associated to each point of a space curve. We denote this triplet, we denote these three vectors, we denote these three vectors by the symbol T, N and B, where T is called the unit tangent, it remains tangential to the curve, we already know about it, unit tangent. The second one, denoted by N, is called the principal normal, and the third is also a unit vector which remains perpendicular to T, N and B both. So, this is called binormal. And these three vectors are in fact form a right-handed system. So, the Frenet trihedron becomes a set of three vectors T, N and B, and this set I will be calling as Frenet trihedron. There is another important thing about the Frenet trihedron, and which is this, these three vectors form a right-handed system. So, moreover, T, N and B form a right-handed system, That means that the vector B is in fact the cross product of T and N. Vector T is N cross B and vector N equal to B cross T. So, they are perpendicular to each other and they form a right-handed system, and since they are mutually perpendicular, there are other relation in terms of dot product. For example, say dot product of T with itself will be 1, dot product of T and N will be 0 because they are perpendicular, dot product of T and B will also be 0 because they are perpendicular. Similarly, you can write down all the relations of N. So, N dot T is 0, you have already seen here. N is unit vector, so its dot product with itself will be 1. n dot b is 0, b dot t is 0, b dot n is 0, and b dot b is 1 because b is also unit. So, these are some relation which naturally hold for the vectors of Frenet trihedron. Okay, now, I will work out their expression in terms of R and S. So, expression for the three vectors t, n and b. So, we have been assuming that there is a space curve in natural parameter S and it is regular. So, we can differentiate R. And so, the first one is already known, we already know that the tangent, unit tangent t is R dash. Okay. So, this you can consider as an expression of t in terms of the derivative of R. This is already known to us. And the second one is n. So, look here, we have just noticed, we have seen that R double dash is a unit vector, R double dash may not be unit in fact. R double dash is a vector perpendicular to t, is a vector perpendicular to t. T or R dash, whatever you call it, and it lies in the osculating plane. We just observed this fact, and it lies in the osculating plane. Why it lies in the osculating plane? Because the equation of the osculating plane is R minus R 0, R 0 dash, R 0 double dash. This scalar triple product is equal to 0, means these three vectors are coplanar, they lie in the same plane, the osculating plane. So, R double dash, R dash and this one, all of them lie in the same plane. So, R double dash we know lies in the osculating plane, it lies in the osculating plane. So, I have got R double dash, a vector which lies in the osculating plane and it is perpendicular to t. So, we introduce the principal normal n as follows. So, this becomes my definition. N is a vector which I assumed is perpendicular to t and b both, and it lies in the osculating plane. So, this is how I look at the principal normal. So, if somebody asks what is the definition of a principal normal, you will say it is a unit vector which is perpendicular to the unit tangent t and it lies in the osculating plane. So, this becomes the definition of the principal norm. Hence, the principal normal n is a unit vector which is perpendicular to t, t means the unit tangent, and it lies in the osculating plane, osculating plane. So, these two characterizing properties of the principal normal really define it. Okay. So, now comes the third one, the binormal. The binormal is simple, it is a vector which is perpendicular to t and n both. So, I can define, so binormal B can be defined as B equal to t cross n. B is equal to t cross n. This definition we have written earlier. Now, we want a definition in terms of the derivative of R.